little tour for a demonstration on just how straightforward and just how nicely the vacuum triode is working. So we have a 120 volt fan. As you can see, it's turning at good power. It is providing quite a breeze, and it's real usable power. Now we'll turn around, and here, as just coming into view, you see 5 100-watt lamps, ordinary garden variety household lamps, brilliantly lit. So there's 500 watts of very real power here, again coming right out of the vacuum. And you see the assembly of very large meters and show you the kind of power amplification that is being achieved by the vacuum triode. Now we're going to come back in. There's the 500 watt bulbs clearly illuminated. The power is rock steady. It's a fairly decent sine wave, very nice and steady, and it's 60 hertz. It's right on the button, just as conventional ordinary power. It's 120 volts or very close there too, and it's 60 hertz right on the button. It is, however, negative energy that is being produced as opposed to the normal garden variety of positive energy. In the lamps, in the resistive load, the negative energy is converted to ordinary positive energy, and that is real heat and real light being radiated away from the lamps. However, while the energy is still in the negative form, in all the circuitry and wires going to the lamp, all of those stay absolutely cool because there is no heating of those circuits. Only in the filaments of the lamp is heat and light produced in the normal sense. And so in those resistive loads, we're translating normal negative energy into positive energy. And you can see that is real power, 500 watts, 1/2 of a kilowatt in a resistive load. Travel back over to the fan, and you see that we have a normal AC type load. That's a normal AC fan. Runs very well on this power. Now we'll come back over to the load, and we want to go up and show you some instrumental measurements. We want to show you how much we're actually putting in to the grid signal of the triode. First, we're going to come right in on this meter here and try to give you a close shot of the actual reading of this meter. Okay, in reading the meter, it shows you that we're putting in right at 10 volts. It's oscillating between 9.5 and 10 volts. That 1 is really a 10. It's on the, that's a 10 volt. Okay, we're going over now and show you the amperage that we're putting in, and hold your hats. That 31.2 is actually 31.2 microamps. We're dealing in the microamp scale, and we're putting in 31.2 microamperes of current. We're putting in approximately 10 volts for the input. And so it's very easy to calculate the fact that there's less than 1 milliwatt, actually down around 1/3 of a milliwatt or so, of power actually going in to power the fan and the 500 watt of lamps brilliantly lit. Now we'll go over and show you some more meters coming in on this set of instruments. Let's see if we can get a better focus and get the glare away from us. Looks like we won't get the glare, but there we are. That is a voltmeter, and it shows that we're putting out about 112.5 volts coming out of the vacuum triode. That's the plate voltage, so to speak, that's output by the device. Coming over to the next meter, this is a watt meter, and you divide it by half, and you see it's reading 1 kilowatt, and so this one here, we get on the right meter. It's reading 1 full kilowatt, so divide that by 2. And so you see that we're putting out 500 watts of actual measured power. Okay, coming on over. The power factor shows 1 as it will in the resistive load. And of course, single phase circuit. You can see now the amperes on this meter being put out by the machine is very clearly, let's give a read on that. We're putting out 4.6 amperes of current. 4.7, a little more precisely, 4.7 amperes of current. And so that is the output current. All of that, the entire output, is being taken from the energy of the vacuum, output by the device, and the grid signal to do that is less than 1/3 of a milliwatt. Less than 1/3 milliwatt signal on the vacuum triode grid, and yet the plate is putting out well over 500 watts of power, 500 watts of the resistive load, and at the same time you see the fan stirring up a nice breeze. This is real usable power. It's stable. It is not transient. It is not noise. And it is not any other kind of spurious effect. This is a real effect. It's all coming from that little tiny box sitting behind the 500 watts of power. Behind the lamps, that little box is putting out all of that power, well over 500 watts, and yet it is receiving less than 1/3 of a milliwatt of input power. This is April the 30th, 1987, at about 10:30 p.m. in the home of the inventor of the very first vacuum triode. This is a most historical occasion.
I will show them some more.
Okay, now for this second demonstration, here we have our 120 volt fan again, rotating finely, stirring up a breeze. Right behind that you see a 24 volt DC motor. In front of that there is a little bit of a rectifier, a little box here. See if I can get my finger here. This is a rectifier. This is a transformer, dropping the AC power down to the 24 volts. And you can see there are two 12 volt lamps in series, brightly lit, showing you that yes indeed we have the full 24 volts. We're showing that this power can be transformed and can be rectified just exactly like normal positive power, except again the power is very cool in the actual lines and feeder circuits. Only in the actual resistive load do you have translation into normal power, but it can be run through a transformer and stepped down or stepped up. It can be rectified, and we can handle the power just indeed as we do normal power. And you see again at the same time we have 4 of those lamps now lit, and so we have another 400 watts resistive load going here at the same time. And if we close up on our little meter here, we'll see that now we're drawing only 29.2, if we get the glare out of there, 29.2 microamperes. 29.2 microamperes. We're still drawing about 10 volts, oscillating between 9.5 and 10 volts to the input of the grid of the vacuum triode, which is that little box right there behind the brightly lit 100 watt bulbs. Now in the lower left of your screen. Again, 4 brilliantly lit, ordinary 100-watt lamps, household lamps. You can see here the 24-volt DC motor. You can see the transformer stepping down the voltage, the 2 12-volt lamps in series, so that we have effectively a 24-volt, the resistance for 24 volts applied across them. And in front of that, then, we are rectifying this power to furnish DC power to the DC motor. And so what this demonstration does is that with very little change to the input to the vacuum triode, we can provide a power which is practical. There's plenty of it. It's a very great power gain. It can be transmitted along lines without any heating. It can be rectified. It can be, we can use a transformer to step it up or step it down. It's a very practical, very straightforward type of power to use, even though we're using negative energy in the lines. And the characteristic, when you switch suddenly power loads of negative energy, you do not have the big flashing and arcing, because that's a positive energy effect. The arcing effect on these is reversed. In other words, it's a cold arc, an arc of cold, so you don't see all of that stuff and you don't burn out the circuits and all that. You can switch the loads suddenly very easily with normal switches. And so this is a very practical power. You can see again the 120-volt fan. You can see here a normal flat pancake type of 24-volt DC motor. You can see 2 12-volt lamps brilliantly lit. You see the rectifier that rectifies the current for the 24-volt DC motor. You can see we're coming through a step-down transformer from the 120-volt negative power line. And you can see we're still providing 400 watts of power in the lamps. And of course there wouldn't be any problem with turning the other lamp on. And you have seen, of course, that we're still drawing less than 1/3 of a milliwatt. We're drawing now 29.3 microamperes of current, and we're still sitting at about 10 volts on the grid. 10 volts, 29.3 microamps, the input to the grid of the triode, and you can see 400 watts of power here, a step-down transformer being operated, a pancake motor being operated, and a 120-volt fan being operated, all from less than 1/3 of a milliwatt of power. The rest of that power is coming out of the surging energy of the vacuum, and this little box that you see right here, solid state, no moving parts, is the vacuum triode that's doing this very practical and historical work here on April the 30th, 1987. And now we're focused on the actual little oscillator that's providing that input power. This is a Hewlett-Packard audio oscillator, model 201CR. The maximum power this oscillator can put out is only 3 watts when it's at full peak power.
Is it 600 ohms?
And it's going out into 600 ohms.
And that would be at 45 volts if you wanted to use 45. How about using 10 volts?
The maximum voltage that this little oscillator can put out is 45 volts. However, as you can see, we're only using 10 volts, as you can see right here on the scale. So we're using 10 volts of power to the grid, voltage to the grid. Right now we have 29.3
Stable, huh?
very stable microamperes on the grid, so we still have less than 1/3 of a milliwatt of power on the grid. And from that we're pulling out of the vacuum from cathode to plate, we are gating and controlling well over 400 watts of power. You can see the four 100-watt bulbs brilliantly lit, and when I get off to the side you'll see just how brilliant they are when the CD readjusts. You see that we're stepping it down through the transformer, lighting the two 12-volt bulbs, going through a rectifier, driving a DC motor which runs fine off negative power, likes it real well, and then the 120-volt negative power is going to the 120-volt fan, which again likes it very well indeed. And so negative power, negative energy taken from the vacuum, is very useful and very practical power. This power can be put into production, can be developed into, for example, a reasonable home power unit, say of 15 kW, and you can see that this box, which we showed you a while ago with 500 watts on it, doesn't represent too much of a step-up problem. We're not dealing with very much a magnitude step-up problem. And so our scale-up problem should not be bad at all. I will mention that the little box in the back, the solid state vacuum triode, see if I can get my hand on this. You can see my hand on it. It is not hot. It's solid state, no moving parts, no vibrations, absolutely rock steady and eminently practical. It is not expensive. Ordinary machining, ordinary parts, ordinary type construction can easily build this kind of a power device. As we said, the closest nomenclature for this device is a solid state vacuum triode. Nature itself is providing the river of current that's flowing from a special cathode to a special plate. And we are only putting in a very small control or gating signal to the grid to gate all the other power that you see being consumed right here. This power can be transmitted, it can be transformed, it can be rectified, it runs motors, it runs resistive loads, and it's a very eminently practical type of electrical power, very safe power, and a very clean power that's waiting right now for development and marketing. The incredible and historic vacuum triode. Okay, here we are again with the equipment shut down. We'll give you a short tour through what is connected and the major types of meters that we have connected so that measurements can be ongoing dynamically. First of all, behind this card, the little box that you see there is the vacuum triode, invented by Mr. Sparky Sweet, the incredible vacuum triode. Now, we've placed over the triode some small strips of metal so that you'll be able to see parts of the pattern of the magnetic fields surrounding the vacuum triode. And as we come back away from the triode, you see we have a load, which is a bank of 5 100-watt lamps. Can be connected to the 120-volt AC output load, 60 hertz. These are ordinary, common household lamps, resistive load. We have various meters. You see the frequency meter measuring the output of the vacuum triode, and you'll find that that's a very rock stable 60 Hertz. Here are some lines. This is the input line right here to the vacuum triode grid. Nominally 10 volts RMS coming into the grid, 60 Hertz, and as you will later see, very, very low amperage will be measured on the microammeter that measures the amperage going into the grid input. So it'll be 10 volts plus whatever this instrument measures. The next instrument here is the voltmeter itself that measures the grid input. And on this one we'll see the 10 volt input. The input signal itself is coming from an audio oscillator, which is a sine wave oscillator. It has a maximum output of 3 watts. That's all you can possibly get out of it. 45 volts into a 600 ohm load. That is what we're using for the input, and as you will see, there will be far less than that 3 watts going into the vacuum triode. Then here are the triode output cables going to the instrumentation, and then around behind the back to the load, to the lamps. We will be feeding a 1 kilovolt, 1 kilovolt ampere, 120 volt kVA, 120 volt transformer. Has dual 24 volt secondary. The loads will be 2 12 volt lamps in series, plus a rectifier, plus a 24 volt DC motor. Here is the rectifier right here, coming from the output transformer, with the 2 lamps in series across the 24 volt output of the rectifier, and with a 24 volt DC pancake motor, 1/8 horsepower, 2000 RPM, which will be energized. Here you see a voltmeter which reads the voltage on the rectifier output. And then we will have a standard 120 volt AC fan load also connected to the output of the vacuum triode. Coming on back around now to finish the instruments, we see a bank of instruments here. We have first of all a voltmeter that reads the voltage of the output of the triode. Then we have a kilowatt meter that measures the actual power output of the vacuum triode. We take a look at the phase. You'll see that that's really single phase current, and everything's in phase. Then the amperes being put out, or the current being put out into the load by the vacuum triode. And finally, coming around here, we have an oscilloscope which will be set up across the output of the vacuum triode so that you can look at the 60 Hertz output waveform. We will show you the waveform on the scope. And that completes the primary instrumentation, with the exception of the frequency counter here, where we actually show that it really is a 60 Hertz frequency output. And so Mr. Sweet will now turn on and energize the equipment, and we'll take you through another tour.
Now turn on the oscillator.
Okay, we're now turning on the oscillator, and we just heard the 24 volt DC motor start up. The 2 24 volt lamps are illuminated, showing you that we're furnishing power to that transformer, stepping it down to 24 volts, going through the rectifier, lighting the lamps, and running the DC motor. At the same time, before we step it down, the 120 volt power is being furnished to the 120 volt AC fan, and as you can see, the fan is blowing up a nice pleasant breeze here on this very warm evening. By the way, this is May the 16th, 1987, at the home of the inventor, Mr. Sparky Sweet. And from the lamps, we want to call attention to a direct ray which is invisible to the eye, but is visible to the tube, the CCD solid state part of this camera. You'll see a very straight beam of some kind associated with each of the lamps. We're still investigating that beam. Okay, the equipment is now energized and ready to be connected. Let's take a look at the output waveform. Let me get down at the right level, and as you can see, we have a very good sine wave in the 120 volt AC output from the plate of the vacuum triode. A very nice sine wave indeed. And as you can see, when we turn to the frequency meter, we'll take a look here and you'll see that we keep counting the frequency, and it's right on 60 hertz. Right dead on 60 hertz. You can see now that the power we are actually furnishing to the grid, this is the voltage. It's about 10 volts. It's oscillating between about 9.5 and 10. And on the microammeter, these are microamps. Right now we are furnishing 7.9 microamperes, and yet we're running 2 motors and lighting 2 lamps. You want to energize the other lamps? Okay, we'll look first now at the bank of meters, and we will see that for the output voltage, we've made a very careful adjustment, and it's right on 120 volts. Right on the button, 120 volts in the output, AC. This is the watt meter. You can't get a good focus on that, so I'll read it for you. Dividing it by 2, we're putting out right now about 145 watts of power. The power factor, of course, is 1. Amperes we're actually putting out is about 1.5. Let me back up. 1.25 amperes of power being output. So we're actually putting out 240 watts right at it now, about 240 watts, and yet we're only putting in 10 volts and 7.9 microamperes. 10 volts, 7.9 microamperes. So the total input is a tiny bit less than 80 microwatts. We'll now energize the main lamps simply by connecting them into load, screwing them in. There's the first 100 watt bulb which goes in. Here's another one, and here's another one, and here's another one. So we've kept the AC motor going, we've kept the DC motor and the DC lamps lit. We have 400 watt bulbs now being powered, and when I come off of this you can see they are brilliantly powered. When the camera is on the bulbs, the CCD steps the lens down so that we can actually get a picture. So we're producing now well over 400 watts. And in fact, if we come in on the watt meter right here, let's take a reading. We're producing 400 and some 80 watts. And as you can see from the meters here, at 10 volts and now 25.1 microamperes, we're putting in only 251 microwatts. 251 microwatts and about 480 watts out. So as you can see, we have quite a power factor gain. As a matter of fact, the gain right now is approaching 1,500,000. For each nominal watt of power input, one would get a nominal 1.5 megawatts output in a bank of such devices. This is May the 16th, 1987, at the home of the inventor, Mr. Floyd Sparky Sweet, and this is the incredible vacuum triode which organizes and gates energy directly from the vacuum itself, producing usable, practical power.
We got Robert Moses power plant up there, yeah, that's lots.
So they really never changed anything, did they?
You say, oh, I got to design a big transformer, and he used to call the cucumber. But that's not an efficient
I
transformer.
know.
Well, let's see now.
You want a light on that, or you want the thing working?
Yeah, I need more light if I can get it, but
Why the hell am I going to get it?
no, that's all right. I'll take it like that.
I can put
What I need you to do is explain what we're looking at here. And
Want me to turn it on?
yeah, and I'll
This is,
we're at the home of Mr. Sparky Sweet. This is 15 May 1987, and we're showing here the conditioning setup to actually make the vacuum triode, to make the pump waves and establish them in the permanent magnet itself to make a permanent magnet vacuum triode. And so you can see here the large coil, which we'll focus in on here a little bit, and the large upright coil here. Inside this large coil, if we can go in there and see,
at the bottom there's another one.
there is another coil which we're not going to be able to see with that light, but it looks about like a spool of wire like this. I get on it here like this. It's an entire spool of wire, number 15 wire, Sparky?
Number 15 wire with a ECR of approximately 4 ohms at 20 degrees centigrade.
Okay. It's about a 0.4 ohm impedance. Number 15 wire, a whole spool of it, is sitting inside the large conditioning coil down on the bottom. Right here we see the SCR as part of the circuitry. There's a light bulb that gives him an indication of the voltage across the capacitor. Here you see he's reduced this conditioning circuit to using only one capacitor. What's the capacitance of that?
This is 1600 microfarad.
It's a 1600 microfarad capacitor,
250 volts.
250 volts,
AC working voltage.
AC working voltage,
DC
DC working voltage. And he has a variac trigger arrangement set up and a potentiometer to adjust the circuitry,
which we're doing now.
which he's now doing, as you'll see by the light bulb.
Right.
And there is the capacitor, a large tuning coil or conditioning coil with a coil on the bottom.
The coil in the bottom is driven by wave-tech oscillator.
He has a wave-tech oscillator driving the coil inside at the bottom
Through a 100-watt amplifier.
through a 100-watt amplifier.
Right. And this determines the natural frequency of the molecular structure. Or
That's the one that you impress in there, right?
that's the one.
when we open the gate in the molecular structure of the domains, whatever frequency we impress with that inside bottom coil is the frequency that's put into the magnet as a memory. In other words, that determines the actual frequency of the pump wave. You might say a cathode to plate oscillating current is established inside the magnet, and by analogy that's what's established to make a vacuum triode.
And the gate here is opened by its pulsating frequency of the capacitor discharge system, which is
There's a capacitive discharge system attached to the large coil. It's being triggered by the variac, and as Sparky is pointing out, that is going...
This determines, of course, the time. This sets the time constant.
Right.
It's the time constant.
This sets the time constant of that, and that's going to determine the gate opening in the triode,
Which is R times C.
which is R times C, the RC time constant.
Right? Which is, of course, the resistance of the coil and capacitance, capacitor, and farads. The resistance of the coil in ohms. And, of course, the time will be in seconds.
X sub L of the large coil is in ohms, and the capacitance is in farads, and of course the time is in seconds for the RC time constant.
Which in this experimental setup, this particular magnet is found to be approximately 10 or 11 hertz, right?
In this magnet, the resonant frequency of that magnet can be shown to be in the vicinity of 11 hertz. Now each magnet will vary a little bit, and you must find the actual frequency for each individual magnet. But it's around 11 hertz for the size of magnets we're using right now in the demonstration device.
And that's determined by, let's see, can you shut that off a second?
Yes. Okay, here we have placed one of the magnets on top of the large coil,
Maybe I can get that to move.
and we're tuning the driver frequency down towards the 11 hertz. This is on the inside coil we're driving now. And when we get down to the resonant frequency of the magnet, you will see the lamination that's been placed on top of the magnet start to vibrate. You'll see it shake and oscillate a little bit, just at the frequency that is the resonant frequency of the magnet. Do a little adjustment.
Well, now you're making adjustment. Make it move.
This is the amplifier. It's tuning the amplifier voltage.
Oh, I unplug this.
We have to plug it in. There's a plug missing
Hold
here.
on. I put the lamp in, I took that out. Now, let's see, I took something else out. Oh. Line, I can see something.
And with me here this evening is Mr. John Bedini.
Okay. Let's see what I'm doing. Okay. That's a sign. Yeah, I guess it's all right. Can't see what the hell's going on here. I got it in. Oh, wait a minute. I took the oscillator out.
Yeah.
Okay, now it's going.
Let's see if we can get that going there.
See if we can get it adjusted right on the resonant frequency.
Just hang on.
We'll see a little emanation wiggling when we hit it just right.
Here. Shut that down a second. This one. I wish I could see this dial. What do you want? Oh, no wonder.
We're getting it set up now for the right resonance range. And that's a sine wave frequency going to this inside coil.
Wait, wait.
And now you
Wait a
can see
minute, hold on.
the magnet should also be
What?
aligned with the Earth's.
Huh? What is it you want?
The long part of the magnet should also be generally aligned with the Earth's magnetic field for best results.
Things that I can't see this in. I can't see where 11 or somewhere it was around 11 hertz before. I can't see it.
Get it for you. Times 10, right? Times 10, 11.
Let's see what I yeah, right there.
Okay.
Is that 11?
Yeah.
Trying to go? Well, that frequency seems to be too high. Where are you?
That's 11. There it is, Spark. Just very lightly.
The magnet is now beginning to resonate. We'll see it just when we cross it right on that. It's a very small, fairly precise spot frequency.
I can tell right away. Yeah, that's... Here, see this one? That may be a good indicator for you. You know? You just hold it here, see? Spark. Just hold it with this hand.
I know about this one.
Yeah, but then you can set this and you can feel it. see? Yeah,
There it is.
there it is. Right? Yeah. You want a resonance, right? Right there.
Moving?
There it
Oh,
is.
yes, that thing's really moving.
Now the magnet is in resonance, and so we have the proper
That's
frequency
12,
to resonate the
about
magnet.
12 and a half.
This particular magnet is resonating at about 12
You were right
and a half
about
hertz.
this, Spark. Each one's different.
Each magnet is a little bit different, even though
Let's see
they're
if
the
we can
same
get it
size.
going a little better.
Maybe 10.
No?
That's good.
No, it's really going there, okay?
That's in good resonance now.
Yeah, I know.
Okay, now you want it absolutely in perfect resonance, right? There you go.
There's the
That's
best
12
resonance we
and
can
a-
get,
12
and that's
and a half.
fine right there.
All right, now let's see.
It's at 12 and a half hertz.
Right. There you go. Now you got both of them locked.
When this one is at, when this one is at 60 hertz.
And now we're putting the
Okay, now you go up with this one, right?
Yeah.
the 60 hertz. I'm sorry,
That's
Sparky.
good right there. If you go off just a little bit to the edge, see?
Yeah, there we go.
The 60 hertz was
Here, I can hold it there.
Now we gotta bring this one up, okay?
with the magnet in resonance at its 12 and a half hertz resonance.
There you go.
Now, gotta bring this up to a stop.
Then we bring up the
Maybe
trigger
about
circuit
60.
Okay.
at 60 hertz,
Right.
which is being applied to the large coil.
There, now it stopped.
And there we are. You can see
Yeah,
the
yes, just
magnet in
wavering in
resonance.
between.
It should be.
Okay, you want to bring it down a little more? Till it stops?
There we go.
There you go.
Wait,
And-
now Now, explain how the 60 hertz is,
Well, it's
the
now,
memory is in that magnet.
With
Yeah.
the magnet at its natural resonance, which for this magnet is 12.5 hertz,
see
the
this
triggered
gets it-
circuit
locks
is
it right in.
putting in
You can feel
spiked
it here. Put your hand
signals
right here.
of 60 hertz through the large
Yeah.
coil, triggered
You can feel
into
the
spikes with certain RC time constant discharge determined by the capacitance and the resistance.
If you go
And
to
that
the top a
impresses
little
the
bit,
60
right?
hertz
There you go.
into the magnet itself as a permanent memory. And so the magnet will have a locked in 60 hertz resonance impressed in it. When it is in its natural resonance, it has a natural window that's opening so the 60 hertz can be put into the actual nuclei of the atoms in the magnetic domains themselves. And once that's done, that magnet
60 hertz, you can't see it.
is conditioned for the 60 hertz condition.
Now,
That's the cathode to plate current. It is now conditioned for a 60 hertz current.
Sparky.
huh?
Everything, even this thing was a rocket. Yeah.
Look at that.
No, it'll just sit there. So you just put it to the edge, see?
Yeah.
Mm-hmm. Oh, that thing's moving. Want to get it going faster?
That's real good right there. That's maximum.
Okay, that's 12, 13 hertz.
At 13 hertz, we now have a maximum in this magnet, as you can see right here.
So it's a little...
We've shown the first part of the conditioning process to condition each magnet individually. And now,
I see what you say, you have to condition this.
the entire magnetic assembly must be conditioned.
And then you put the whole thing
And so, as you can see,
Otherwise, you won't know where you're at, will you?
in. No.
now as you can see, Sparky has assembled the two magnets over the aluminum box that is the holder,
And this is in positive mode.
and the ends must be kept in the same direction they were in when they were conditioned before.
Attractive mode. Now we put this in there.
And they're in the attractive mode. They're then placed in the box onto inside the large coil, sitting down on the other coil, so they're about in the center of the large coil. They're approximately centered in the large coil. With the box in that position, then, the final conditioning process is ready. At this point, you can hear the chattering as the beat frequencies go, pump waves are going, and all it remains to be done is to turn on the 10 hertz, 10 volt, 60 hertz driver signal,
Nothing's moving.
and at that point, now let's see, your driver signal is in the small coil this time, right?
Yeah, that's the small coil, 10 volts. Well, in the case of the one we have inside is, the power to drive it is 3/4 of a milliwatt.
Right.
1/3 of a milliwatt. Right? And we don't change that no more, right?
You don't change any frequencies.
You don't change this thing here, right?
Everything stays the same after we get a good wiggle on the magnets.
Yeah, and you put the magnets down in there, just leave it on.
Put
the
the
magnets
assembly
down
in there.
Put this whole assembly in there, and then you hit it with the frequency, 60 hertz. 60 hertz
Boom, that's it.
is the memory in there.
Yeah.
It stays there, right?
You don't touch anything.
Now to activate it, you need a signal of 10 volts into the particular wire. So,
Once
which
it's,
is- which is not shown here.
right,
10 volts at 27 to 30 microamperes
right,
will drive 500 watts of power out.
right.
So that's the conditioner.
You have to take and do it with the two magnets, you know.
Mm-hmm.
Okay? To find out first what that,
Hole is.
no, we find out first what the frequency is, the natural frequency, the magnetic resonance frequency.
With the iron bar, yeah.
Find out what that is. Right. Now, I found on the other one that I just took the two magnets. They were bigger magnets than this, and I put them together. Put them together like that. Of course, now I got them together, I can't get my shirt out.
Slide them apart. There you go.
I took them like that, and I put them like that.
Okay, so you mark the ends
I
now.
mark the ends, so they go back together the same way.
Mm-hmm.
But I found what the frequency was. Now, what it'll do, it'll average out the goddamn frequency, the goddamn natural resonance of this one and that one.
Right.
It'll average it out, right? So what you read on here, right, is the basic, resonance, magnetic resonance of the magnetic domains, right? That's there. So you know what that is, right? You don't do nothing but you know what it is. So you take them off of there and you put them on this box. And you put the whole assembly down in there.
Right.
Right?
But
Now, don't change nothing. Leave it right at that frequency. Right? Leave it at that frequency while it's down in there. Okay? Then hit it with the 60 hertz. The 60 hertz will go in there and stays in there.
Right. And then you can shut the 60 hertz off, take it out.
Forget it. Now you keep the magnets the same as they are. Remember though that you did it with this kind of air gap. You put one on the top, one on the bottom, stuck them down in there.
Right.
But don't change this.
Right.
Because this has to open it up while it's down in there, not when it's up on here. This man tells you where that frequency is. It has to open up the nucleus when it's down in there. In the middle, it has to be in the middle.
Right.
It's the maximum field strength in the middle. And you put them like that. And you just stick them in there. It's kind of, I had a compass. I was oriented in the north-south position.
Right.
With the north pole
Towards the north. Towards the south pole of the earth. Right?
Orient them with the magnetic field of the earth.
That's what I did.
Okay.
I put it down in there like that. What? In the sun. All right. Now this is on.
Right. So it's rocking.
That's on. Now
Bottom
you
coil
hit
is on.
Now you hit it with the frequency.
And that's
Now
it.
That's it.
That's it. You can load the coils and go.
Go.
Just hit the big coil with the frequency, right?
That's
Yeah.
it.
The pulse.
Yeah, and that's it. You don't have
That's
to
it.
do
At that point, the conditioning is finished, and you now have a permanent magnet vacuum triode, the incredible invention of Mr. Sparky Sweet. This is May the 15th, 1987, in the home of Mr. Sparky Sweet in Sherman Oaks, California.